One single structure, standing quietly across a river, generates enough electricity to light up an entire city of millions, and most people have no idea how it actually works. It holds back a wall of water so massive that if it failed, entire towns downstream could vanish within hours. So how does a slab of concrete turn something as simple as falling water into enough power to run hospitals, factories, and millions of homes? To understand the answer, you first have to understand what a dam actually is, not just a wall, but one of the most powerful machines ever built by human hands. At its core, a dam does one simple thing: it stops moving water, and stores its energy for later, like a battery the size of a mountain. The water held behind the dam is called a reservoir, a man-made lake that can stretch for miles, sometimes holding trillions of gallons of water. Every drop of water sitting in that reservoir carries stored energy, waiting silently for the moment it is allowed to fall. That stored energy has a name, potential energy, and the higher the water sits above the dam's base, the more powerful it becomes. But here is where it gets stranger: the dam does not create energy at all. It simply lets gravity do work that would otherwise go to waste. When engineers open the gates, gravity pulls the water downward through massive tunnels called penstocks, sending it rushing toward the base of the dam. Inside those tunnels, water can move fast enough to launch a car, all before it ever reaches the machine waiting below. That machine is the turbine, a giant wheel of blades, engineered to spin at incredible speed the instant the water strikes it. Some dam turbines weigh over 300 tons, yet they can be spun into motion by nothing more than falling water. As the turbine spins, it turns a shaft connected to a generator, and this is the exact moment mechanical motion becomes electricity. Inside the generator, magnets spin past coils of copper wire, and that motion alone is enough to push electrons into motion, creating an electric current. What nobody expects is just how much power a single spinning turbine can produce, enough to supply thousands of homes from one machine alone. A large hydroelectric dam can contain a dozen or more of these turbines, all spinning simultaneously, all feeding into the same electrical grid. The electricity generated deep inside the dam travels upward through thick cables, into transformers that prepare it for the journey ahead. Those transformers boost the voltage dramatically, allowing electricity to travel hundreds of miles through power lines without losing its strength. From there, the power spreads outward, into substations, into neighborhoods, into the wires running through the walls of homes people have never thought twice about. A single major dam can generate enough electricity to power several million homes at once, all from something as simple as water falling downward. Some of the largest hydroelectric dams on Earth generate enough power for more than 2 million homes simultaneously. To put that scale in perspective, consider the Three Gorges Dam in China, the largest hydroelectric power station ever built, generating power equivalent to dozens of nuclear reactors combined. In the United States, the Hoover Dam once stood as an engineering wonder of its era, still providing electricity across multiple states nearly a century later. On the border of Brazil and Paraguay, the Itaipu Dam can at times generate enough electricity to power an entire country by itself. Together, the world's largest dams generate more electricity than the entire population of some continents could ever consume on their own. Not every turbine works the same way. Engineers choose between different designs depending on how much water flows and how far it falls. Some turbines are built like giant propellers, ideal for enormous volumes of water falling only a short distance. Others are built like sealed spiral shells, designed for water falling from great heights under intense pressure. But here is a secret most people never learn: some dams do not just generate electricity, they also store it. In a method called pumped storage, dams use surplus electricity to pump water back uphill into a reservoir, essentially turning the entire structure into a giant battery. When electricity demand spikes, that stored water is released again, generating power almost instantly, exactly when the grid needs it most. This makes hydroelectric dams one of the most important partners for solar and wind power, storing extra energy for the moments when the sun sets or the wind stops. But producing electricity is only half the story. The dam itself has to survive forces powerful enough to crush almost anything built by humans. Behind the dam wall sits millions of tons of water, pressing outward with relentless, constant force, every second of every day. Engineers design dams with immense curved or sloped walls specifically to redirect that force downward into solid bedrock, rather than letting it push the structure over. But here is where the real danger begins, because water is not the only thing a dam has to fight against. Time itself is an enemy. Concrete can crack, steel can corrode, and small leaks called seepage can quietly weaken a structure over decades. This is why modern dams are covered in thousands of sensors, constantly measuring pressure, movement, and temperature, watching for the smallest sign of stress. Engineers can now detect a crack forming inside a dam long before it becomes visible to the human eye. Some sensors are sensitive enough to detect movement smaller than a single millimeter across a wall hundreds of feet tall. Every dam also includes a spillway, an emergency overflow system designed to release excess water before pressure becomes too dangerous to control. Without spillways, heavy rainfall or rapid snowmelt could cause a reservoir to overflow uncontrollably, putting the entire structure at risk. What most people never consider is that a dam is not just holding back water, it is constantly making decisions about how much to release, and when. Operators monitor rainfall, river flow, and weather forecasts from hundreds of miles away, adjusting the dam's output almost like a living machine. During periods of heavy demand, more water is released to generate extra electricity. During quiet periods, the dam holds back, conserving its reserves. This flexibility makes hydroelectric dams unlike almost any other power source, able to increase output within minutes, not hours. While other power plants can take hours to adjust output, a hydroelectric dam can respond to sudden demand within minutes. That is why dams are often used as a backup system, stepping in instantly when other parts of the power grid struggle to keep up. The story of these machines does not begin with electricity at all, it begins with a much older, simpler goal: controlling floods. Long before anyone thought about generating power, early dams were built purely to hold back rivers and protect nearby towns from flooding. But here is where things changed forever, the moment engineers realized that same stored water could also generate power. In the late 1800s, the first hydroelectric plants began appearing, using small waterfalls to generate just enough electricity to light a handful of buildings. Within decades, that small idea grew into some of the largest construction projects in human history. Building a major dam can require millions of tons of concrete, tens of thousands of workers, and years, sometimes over a decade, to complete. Before a single ton of concrete is poured, engineers build something surprising: a miniature working model of the entire dam and river system. These scale models let engineers pour miniature floods, testing exactly how water will behave decades before the real dam ever exists. Modern engineers go even further, running computer simulations that model earthquakes, floods, and decades of wear before construction even begins. Every possible failure is tested virtually first, because on a structure this size, there is no room for a mistake discovered too late. Rivers often have to be temporarily redirected during construction, forcing engineers to build entire diversion tunnels just to keep the site dry. Some of the largest dams ever built required so much concrete that the material itself generated heat while curing, forcing engineers to cool it artificially for months. Engineers pumped cold water through pipes embedded inside the concrete for months, just to stop the structure from cracking as it hardened. Despite all this engineering, dams are not without controversy. Massive reservoirs can permanently flood valleys, farmland, and sometimes entire towns. Communities have had to relocate entirely to make way for new reservoirs, a trade-off between progress and the land people once called home. Dams can also block the natural migration of fish, disrupting ecosystems that existed in these rivers for thousands of years. What nobody expected was just how far engineers would go to solve that exact problem. Modern dams now include structures called fish ladders, a series of stepped pools that allow fish to swim upstream around the barrier. Some dams even use specialized elevators, physically lifting fish over the structure to continue their natural migration. These solutions are not perfect, but they represent decades of effort to balance human energy needs against the natural world. Despite the challenges, hydroelectric power remains one of the cleanest large-scale energy sources on Earth, producing electricity without burning any fuel at all. Unlike coal or gas plants, a hydroelectric dam produces massive amounts of electricity while burning absolutely zero fuel. Once built, a dam can continue generating power for over a century, far outliving almost any other type of power plant. But here is the question few people ever ask: what would actually happen if a dam this size ever failed? Engineers design dams to withstand earthquakes, floods, and decades of pressure, but is any structure ever truly failure-proof? This is exactly why monitoring never stops. Teams of engineers work around the clock, every single day, watching for the smallest warning sign. Redundant systems, backup spillways, and constant inspections exist specifically because the consequences of failure are simply too great to risk. It is this obsessive attention to detail that has allowed the world's largest dams to safely operate for generations without incident. Somewhere right now, deep inside a dam most people will never see, a turbine is spinning, converting falling water into the electricity lighting up a city. What nobody likes to talk about is what happens when the water itself starts to disappear. Prolonged droughts can drop reservoir levels dramatically, forcing dams to generate far less electricity than they were designed for. Some of the world's largest reservoirs have fallen to record lows in recent years, a quiet warning about how climate patterns are shifting. Engineers are now redesigning dams to operate efficiently even with less water, squeezing more electricity out of every drop that falls. At the same time, some smaller, aging dams are being deliberately removed, allowing rivers to return to their natural paths after decades of being held back. It is a strange balance, building bigger, smarter dams in some places, while tearing down smaller ones in others, all in the name of a more sustainable future. That electricity will reach hospitals keeping patients alive, homes keeping families warm, and factories keeping economies running, all from one carefully engineered structure. It is easy to flip a light switch and never think about where that power came from, but somewhere, a river is doing the work. The next time the lights come on in an entire city, remember, it might all trace back to a single wall of concrete, quietly turning falling water into power for millions.